so I'm back. Sorry for this. I guess I had a computer issue. So let me reshare. Lab 5. Look in here. Then. Okay. Spin video. Good. So yeah, we're discussing sets. So I hope you are able to see and hear me now. So the union of A and B, try to write. So simply you look into the elements that are either here and here, and you construct another set that is basically the superset that combines both. The important rule here is you should have no repetition. For example, if we have 15 in A and 15 in B, the new resulting set, which you can call C, only has 115, not 2, because the general rule of a set is with no repetition at all. And you have to take care of this because this will affect the way you code it, right? Intersection is, as I was saying, like the elements that are in both cases. So in this case, A and B, you look into what elements are in both. So you have 15 and 8, 15 and 8, and this gives you the intersection, right? And if there is no intersection, simply you return an empty set. That means we should somehow be able to represent or model an empty set, as we will see right now in the starter code. The last thing that we should handle is the difference between two sets. The difference is the elements that are in one set and not in the other one. For example, the difference between A and B is the elements that are in A and not in B. So 3 is not there, so the difference gives you 3. 8 is there, 14 is not there, so you write 14, and then 15 is there. So the difference between A and B, or written as like this, gives you 3 and 14. Good? So this is basically the, and by the way, the order matters. So the difference between A and B is not equal to the difference between B and A, right? Because B difference A is the elements that are in B, not in A. Good? So this is the quick review of the simple math behind the lab. Good. What do we want to do? We want to leverage our knowledge, given now that we are a little bit experts on linked lists. So we want to represent sets using linked lists. Good. So why? Why not using arrays, for example? The main point is to simplify the operations, all these operations, as you will see in the lab, the union, intersection, difference, it will be much faster if you maintain an ordered linked list. Because, for example, if you are searching for a certain element in an ordered data structure, or sorted data structure, it's much easier than if you know it can be anywhere, right? So we will simply write a sorted linked list representation of the set. So as we know from the lecture, to have a linked list, you have first to have the class of the node, right? So you are already given this in the starter code, which we also wrote in the lecture, where your single node has the value. And because we said we deal with sets of integers, then it's an end value. And then again, the link to the next node. Good. And then the constructor that basically initializes this. What you are required to do is you are required to use this to have a class that is a sorted linked list. And then this sorted linked list should represent the set for the outside world, right? Another thing to reflect on the ADT and the encapsulation we have been discussing for object-oriented programming. Right now, internally, you have an implementation of a data structure that is SLL, right? Previously, we said we are using the linked list to represent a list, right? Like a general list. Right now, so the user can use our class to represent a list. Right now, we are using it to represent a set, right? While set really is a different math branch, has its own operations that are completely different than lists, right? So as you can see, the good thing about ADT, which is disassociating or decoupling the actual implementation from the upper level or the abstracted or the ADT type that you want to represent, is something that will make you use the same data structure across different ADTs, right? The same single linked list you can use for like representing a list, a set, or even other things, right? Good. So now let's go into some of the lab specifics on how to do this. So you are already given this SLL node, and you are also given the placeholder for the SLL set class. Good. And then this SLL set class, so if I, let me hop there to the Eclipse. Oh, I need to write because I restarted. Okay. Eclipse. Okay, so until it opens, let me continue with this and then we'll go there. So you are already given the SLL set placeholder class. The instance variables are already defined to you. Simply, we have two variables. Both are private. The first one is an integer representing the size of the set. How many elements do you have in the set? Well, one question, why do you think this variable is useful based on what we discussed so far? What do you think? So why do we need to represent the size of a set? Know how many nodes? Yes, that's one thing. Sure, you can use it simply to know you have how many nodes, but that's a little bit lower level implementation thing. So what is the upper level idea? What is the abstract idea? Why do I need to know how many nodes I have, right? One possible application, for example, is this can help you to represent the empty set we discussed, right? If my size is just 0, that means I have no elements, which is representing the empty set, right? Because it's number of elements. Well, yeah, so why do I need to keep track of the number of elements? Easier to access the nth element. This is an answer that I was looking for because it's incorrect answer, Yanhao, because it's not like an array, right? Remember, in a linked list, even if you know that, for example, you want to access the nth element, you don't have a pointer to this, right? So the only thing you can do is you move again from the head until you reach there, right? Good. Okay, good. So yeah, the first one is defining the size of the set. The second one is defining simply the head, which is a reference to the beginning of the linked list. And I guess by now you know pretty well why do we need a head pointer or a head reference to the first element. Without it, simply we don't have a linked list that we can traverse or do any operation on. Good. And then, if you remember when we discussed classes, we said you think of the model, the representation, instance variables, and then constructors, right? So here we have two constructors. The first one is the empty one, which is the default one. It takes no input parameters, and it should construct an empty set. How do I construct an empty set? You should think about it based on what we discussed, right? The second one is you initialize or you allocate an object of a set, but it takes as an input a sorted array, so it gives you an initialization for certain number of elements. So for this sorted array, I might want to visualize this to you to make sure you understand. Okay, here, and let me share that. So I hope you are able to see my my whiteboard. So simply I have initially no linked list, right? So it's empty at the beginning. My head is null, right? Then I take as an input this sorted array in an increasing order. So you have something like 1, 3, 6, 8, 10, or whatever, right? And I want to use this to initialize my set, or as a data structure, my linked list. So what can I do? How I should approach this problem? What do you think? By the way, from the lecture, you already have the full knowledge to know how to solve this problem in an easy way, right? You have number of elements and you want to construct this in a list, right? It's a completely equivalent thing to just say I want to do multiple insertions to the list, right? And we discussed how to insert using different methods in the lecture. Create a node for the fifth element. Yeah, you need to create a node for all the, I guess what you meant, Nicole, is for the 5 elements, and then, or for fifth element, and then work back. That's also a way. That's for sure a way. So you can either start from here, which might be the logical, natural way, or even start from here, but then each time you need to update the next. Both would be correct. But simply the idea is you want to do a loop over the length of the array, right? So you loop over the array, which is a sorted one. Then in this loop, each time you create a node, in second, attach it to the list. Is that clear? One thing remains to be done. Right now, we created the linked list. This is what we discussed in the lecture. But here in the in our set class, we keep track of something else, right? Which is the size of the set. So you also need to update the size, right? Let me write this. Correct? Do you have any question in this? So in this second constructor, I take a set of inputs. So simply, if I visualize this, what I'm going to do is create a node. Let's say we take Nicole's suggestion as starting from the end, but both would be right. Because this is the end, this would be null. I put the value 10, and then simply the head will be here now because it's just the first one. And then create the other one, make the next equal to the head, and then update the head, right? And then do exactly the same thing for the sex, do this, and then bring the head here, etc., etc., etc. Questions? Maybe you repeat, why do we need the size of LL? So we need the size because, first of all, it's easier to check. It's easier to check whether you have an empty list or not, right? It has no elements at all. Well, can we do it without the size? For sure. It just makes your life easier. It's not a necessary functionality, but it facilitates the way you operate on the single linked list, or generally like the set, because now we are talking about sets, right? Good. Well, so is there any question about this constructor then? So going back to after, so instance variables, constructors, and then the methods themselves. So those methods should either apply or deploy the things we do in the that we discuss in the math, like intersection and union, etc., or helper methods that help us do these math operations as well. So everything will end up being servicing those math operations we want to conduct on the set, right? So the first, so before jumping into the methods, we said special kind or special type of methods are the getters and setters, right? So here, because we have a variable that's called size, so we define this as get size, right? Which simply just returns the size. So this is a getter here. So again, just to make sure you guys have, I want to make sure this is very, very clear for you, because this is the way you should approach any class or creating a class-based or object-oriented based project in any programming language. So first of all, the modeling, which means you take the real life example, here in our case, the math set and the operations on the math set, and then model it as abstract data type and implementation of like data structure. After the modeling, you write your class starting by instance variables, which will represent the attributes of the set. Then constructors, then setters, getters, which is the interface. And then finally, the actual operations in the methods, right? This is the way, this is the procedure that you should follow for any object-oriented programming project. Good. So let's look into the methods. One of the methods we want is, and we have done this also for the matrix class, it's a kind of a utility method, which is the copy method. You want to return a deep copy of the set, And as we discussed in the previous lab, deep copy means it's completely associated in the memory. So for example, if I have my set here, and there is, let's say this is set 1. If I create a completely different place in memory, allocate it, and then copy all the elements from here to here, and then I return another reference set 2, this is called a deep copy, right? Why do we call it deep copy? Because simply if I just copy the reference itself to another reference, well, I didn't replicate the memory. So any operation on this will change this. While a deep copy is a completely other copy that is disassociated or decoupled from the original copy, right? So when you see this word or terminology, you know you have to create your list element by element and then copy the elements. Let me see questions here. How do you create the LLM in forward direction? So let's keep this discussion for now on how it's a different way. It would be exactly the same way as you do it in the opposite direction, but I will come back into this at the end, but after I make sure I cover the remaining of the lab. Okay, good. Perfect. So how do we do a deep copy? I guess you guys have already done this in the current lab. You simply should define or declare a new set and then start copying all the elements, going through all the elements of the original set, which is this set, and then copy it into copy the value into the new set, right? And then is in, which is the one that is similar to the traversal or search we have done in the previous lecture, it returns true. So you take a target value and you search the list or the set for this target value. If you find it, then you return true. This is why it returns Boolean. Otherwise, you return false. Well, one thing you can leverage here is you know that you have a sorted linked list. So you don't need to search the whole linked list. Where should I stop if I know that I have a sorted linked list? What do you think? So I start from the head, as we have done in the lecture. I move one by one until I find my target, or what? What is my stopping criteria? Yeah, if the value is larger than the target, that means you have already passed the range that you can find your value in, right? Because it's sorted linked list. Thanks, Keith. And this is one advantage of having your data structure as sorted. Good. And then the other, so all of this is kind of utility things, searching and getting signs copy. And then now we come into operating on the sets themselves. So we want to add now a value, or attach a value, or insert a value into our set, right? If it's not there. So to do this, there are some special cases. So it's not completely equivalent to do that. Oh, come on. No, I cannot. Okay, that's fine. So what we have discussed before is just inserting a certain value into the linked list after or before at the beginning. This is what we have done in the lecture. The point here is, or what might be the new challenge, is you know that your set is sorted, right? And the second condition, it has no repetition. So you have to make sure of these two things. How to make sure of these two things? The first one is you check if your input, which is the value, let's say it's written like add int value. So I need to check if v is there or not. So I start from the head. Then check. And what would be my checking condition? The same condition that Katie mentioned, which is you keep moving until you find that the current value is larger than, so dot current, this is the index dot current value is larger than the value. That means you didn't find it. And then in this case, you insert, but you have to keep track of the order. So to pay attention to order. Then the fourth thing is, if this condition, so if you keep moving until you really hit the value itself. So if you find that the value is equal, then, well, it's there, so you do nothing, right? So is that clear? So simply I have different cases. First of all, if the value is already there, because I need to keep the set without repetitions, so I don't add it. Assume it's not there, then I want to add it. Where should I add it to keep the sorting? That's the important question we should discuss, right? So how to make sure I keep my set sorted, right? And this will also explain to you why we use linked list, not an array for this. Because keeping the array sorted when inserting is really a big problem. You have to shift everything afterwards. So assume, for example, I have something in this array 5, 7, and I want to insert 2, right? So what should I do? The final output should be something like 1, 2, 3, 5, 7. Put aside the problem that you want to increase your array size, but assume we already have a large array. But now by inserting 2 here, everything afterwards should be shifted, right? So in worst case, if you have n elements, you have to do n shifting operations, right? Why? And I guess you have already seen this in lab 3 of the C code where you wanted to withdraw a student, for example, right? So now with a linked list, this is really an easy operation because the linked list has no notion of locality. They are not associated together. They are separate in the memory. So the way those exact values would be represented in the linked list, something like 5, and then, well, 7, right? So now if I want to insert 2, what would be the final expected output that you want? Simply you will create the 2 here. And then you know that 2 should be between 1 and 3. And this is a condition you have to check. And then what you would do is do the insertion we have discussed before, which is first update this in order not to mess this, and then move this here, right? So create the node, update the next of the node, and then finally move the previous one, right? And then you are done. Yeah, now I don't know, to be honest, how Python lists are really implemented in detail. So, well, I know you can really append them, but I'm not sure if they use linked lists or other data structures, because linked lists are not the only data structure that you can really use to append stuff, right? Good, but is that clear? So simply this is also an application that shows you why linked lists is easy to insert, add than arrays, right? Which we discussed theoretically at the lecture. Good. Okay. And then remove would be a similar operation to the add. First of all, you need to find the value. If the value is not there, you do nothing. If the value is there, you have to delete it. Remember, we discussed how to delete from a linked list in Wednesday's lecture. You cannot just directly delete it. You have to make sure. So first of all, how do I delete? You have to make sure the input reference is removed, right? But if you just break the input reference, the remaining items of the list will be broken. So if you remember, you need first to update the previous next to be this node next, right? So I'm not sure if you can imagine what I'm saying, but assume, for example, here, I want to delete like the 3 element. So what should I do? I know for sure I want to, let me delete the insertion for now. I know for sure that I want to break this link, right? But how to break this link? If I just assign it to anything or break it, I lost everything, including the 5 and the 7. So what should I do is to say this equal to the 3 next, and then now 3 has no reference, which means the garbage collector will delete it, right? Good. Another reason why you can leverage the sorted set is simply for searching for this V. You don't need to go to the end of the list. As far as you exceed the value, for example, if the current value is larger than V, the remaining ones, all of them, you know they are larger because it's an increasing order, so you don't need to continue searching, right? So it increases your performance. And then finally, some of the ones that now operate in 2 sets, the union and the intersection and difference. So the union of 2 sets, let me visualize back again. Assume Let me take the example from BDF here. So I have 3, 8, 14, 15. B is 2, 8, 9, 15. 2, 8, 9, 15, and 100. So I want to create the union list. I know that these two are represented in this way. This is the head of A, and then it has 3, and then 8, and then 14, and then 15, right? And this is null. I know also B is represented like this. And that's B. So how should I approach the union, knowing that I have a sorted linked list? First of all, union takes the values that are in both, right? And you have to keep it sorted. Put this in your mind. So where should I start? The first thing is you should determine your starting point of the new list. For example, in the new C list, what should be your starting node? What do you think? Should be 2, right? Clear from this example. So how did I know this? You really compared, Mark compared this and this, right? So the first thing is you need to compare your heads to know what is smaller, and this should be your starting element, right? So you keep here 2 indices. Let's call this set 1 and set 2, or index 1 and index 2, whatever, it doesn't matter. And then you take the value that is smaller, put it here. But once you put it here, you should advance your set 2, right? To know which element you should compare, right? So I should move it here. And then you create a loop that as far as you still have elements in both or in any of the lists, so your loop should be as a pseudocode, your loop should be while set 1 is not null and set 2 is not null, then you still have elements to compare, right? So that's the first case, right? And then each time you should look into which one is bigger. Those who, if you remember the question where we solved the efficient vector, sparse vector representation in lab 2 in C, it's a very similar idea, right? So simply you have 2 indices in 2 linked lists. You keep moving. Once you copy a value into the new list, you advance the one that you copied the value from. To visualize, I have already copied 2 here. Then I moved set 2. Now I need to determine what is my, let me use the same color. What is my new one? I should compare this with this, which is simply comparing set 1 dot value with set 2 dot value. Is 3 larger or 8? 8 is larger. That means I should take set 1. So I copy the 3 here. And then, as you might imagine, I should advance set 1 here, right? And then again, repeat the operation, compare this with this. If it's equal, I only copy one of them, or if it's larger, I copy the small, like the smaller one. And then that means I take the 8 here. Well, here there is a special case. If they are equal, what should I do with the set 1 and set 2 index? What do you think? Advance both. Exactly, Mark. Thanks. So that means now if both are equal, you should copy only a single value because there is no repetition. And in this case, you advance both. And then you continue the operation. Well, that's one case, which is where both sets still have some values. Once you exit this loop, one of the lists or both are ended, right? That means now you should take the values of the remaining list. So you should also write the condition. Now, if set 1 is not null, right? That means that's the case where set 1 has elements. then you copy the remaining values of set 1. Else, you also copy the remaining values of set 2, right? Ishmael, the way you are implementing, wouldn't this set be decreasing order? No, I'm taking the smaller values first because I'm starting from the head, right? If you start from the tail or from the end, then you take the ones that are larger. But here we are starting both from the head. So if I'm copying the smaller, 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 it will be an increasing order, right? Because as you can see, 2, 3, 8, right? So that means it's an increasing order. Okay, so I hope that's clear. And then intersection would be a similar idea, while you really don't copy the values that are not in both. You copy the values that are in both, right? So if I do the intersection for this example, like your structure, by the way, should be the same. While the set 1 and set 2 is not null, and then you keep proceeding your set, but then you are only checking for equality, right? And because you know that both sets are in order or they are sorted, that means once you hit, for example, here, this is 2 and 3. What does it mean? It means that set A for sure doesn't have the element 2, right? So this one is not going to be copied, right? And then it still means that B might include 3. So I should advance set 2. Here I find this is 8. What does it mean? It means that B will not have 3 for sure, because 8 is larger than 3. Then I should advance set 1. I come here, I compare 8 and 8, perfect. I copy this one. And then if you find something that is equivalent, what you should do, again, as Mark said, you should advance both. So set 1 will be here, set 2 will be here. Compare this, 9, 14. 9 is smaller, which means set A for sure will not have 9, but set B still might have 14. So I should only advance set 2. I come here, that's 15. Compare 14 with 15. 15 is larger, which means for sure B doesn't have 14. So I advance set 1. I come here, 15, 15, perfect. I copy 15. And then next, I advance both, that's null, I'm done. I will move to the part of the code where set 2 still has elements. Well, if you are done in this case and that's intersection, you are really done, right? Because you know for sure one of the set doesn't have any other elements, and then you are done with null. So does this visualize to you the operation of how to do the intersection as well? Questions? The test cases will be done the same way. Yes, for sure, Ishmael. Yeah, it's exactly the same way as lab 4. Yeah. And you will be given this. I will move to the starter code right now and hopefully take like 3-4 minutes look into it with you. So I guess we will go over time this time. So I would appreciate if you bear with me for 5 extra minutes or so. Har Sahib, for the lab 4, for the last question. So let's leave lab 4 questions for now. Let's continue with the flow, and then at the end I will stay for taking lab 4 questions, okay? Good. So I hope this clarifies union and intersection. It remains to look at the difference, right? So again, what is the difference? Going back to this same example, let me go here. Now I'm looking for the difference between these two sets. Let's say I'm looking for A, difference B, then the elements that are in A and not in B. Those I know for sure they have to be 3, 14, right? But how to get this, right? How to know this? Let's follow the process similar to the union and the intersection. I will start from the head back again. I have set 1 and set 2 indices that will move forward in the set. And then given that I'm looking for A, so the elements that are in A and not in B, what I would do, and by the way, that's very similar to a question that some of you got in the exam, where you were asked to check, you got 2 arrays as an input, and you were asked to check the intersection, sorry, you were asked to check the elements that are in X and not in Y, right? And you return these. So what you would do, you would need a nested for loop, or in this case, you need a loop that goes through both indices. Take every element in the original one. Back there in the exam question, you had to check for every element, all the elements here. Here, we have a little difference, which is we know that both sets are sorted, right? So I don't need to search the whole array. I only need to search until I hit a value that is larger than this one. So let's see how I do this. I would start with 3, the first, the head element here. So set 1 is at the head. I start looking here. That's 2, smaller. It's not the value, so I keep continuing. That's 8. Well, that means for sure B doesn't have 3, so I write 3 here. Then let's look into the second element. I move set 1 here, and set 2 is right now at 8. Compare this with this. Well, 8, 8, it's there. That means 8 for sure doesn't have to be here. And then I advance both. Set 1 will be here. Set 2 will be at 9. Compare 14, 9. 14 is larger than 9. That means B might still have 14. So I advance set 2, go to 15. 15, 14. 15 is larger. For sure, B doesn't have 14. So I write 14 here. And then I advance set A. That's 15. 15, 15 is there. So I need to advance both. Well, done, done. Does this help? Like going through an example with you guys, does this help? Okay, okay, good, good. So questions, do you have any questions? So now we are done with basically all the labs that we want to do, right? Sorry, not all the labs. So we have done with all the methods we want to do in the lab. The remaining thing is I want to, if you don't have questions, I want to jump into the starter code. For sure, AK, I guess you will be confused. So again, my advice is start first of all with the linked ADT and linked list lectures, especially the example we have done last lecture. Try to write it down yourself. If you do this, and then you watch the tutorial video, and then you start writing your code, you save yourself like I guess half of the effort that you need to think about, right? Because you know how to approach the algorithm based on the tutorial. You know how to write linked list methods and check the special cases, because something we didn't discuss yet is, for example, what if any of these lists are empty, right? Or they have a single element, or like these kind of special cases we have went through in the previous lecture. So you have to keep checking for this. So if you write the example in the lecture video, you also know how to implement these, including the special cases. And that's all what you need to know about the lab, right? Good. So if there are no questions, let me jump into the starter code quickly. So here, oh, I guess that I was looking into lab 4. So let's look. I hope you are able to see my Eclipse. That's lab 5. We have here 3 classes. Let me see if I can, oh no, I cannot make bigger. So it's SLL node is the one that is given to you, which is simply just the node with the one that constructs a single node. And then SLL set is the main class that you want to write. As you can see, you are already given the instance variables, the size and the head, and all the prototypes for the methods. Here, the methods are simply just returning empty things and -1 or whatever to be able to run the test cases out of the box, but you need to write the implementation and modify the return to make sure you have the correct value, right? Here, let me see if I have a test for all of them. Well, that's relieving. Well. Yes, good. So that's perfect. So here you will be doing the test. So first of all, before the test cases, let me go through the methods we went through in the lab document. So those are the constructors, right? So here, the constructors, getters, we have a single get, and then we can call utility methods. So the copy is in, add, remove, and then here, methods operating on 2 sets. Now, if you remember from the previous lab, if you want to operate on 2 sets, what do we do usually? You take one of the sets as your input argument class, which is that, right? The one that comes as you as an input. What is the second one? The second one is the one that you are in right now, which is this, right? These are your two sets, and then you return a set that represents the union, right? The same thing for the intersection. You take one as an input and you have the this, and difference is exactly the same thing, right? Questions? Okay, so the last thing is test cases. So you will see that we have test cases almost for all the methods. Again, what you are required to do is for any method you write, you have to have at least one additional test case, right? And again, to make sure you guys have the mentality, think of the corner cases. For example, testing if the set is empty, if the intersection returns an empty set, etc., etc. Do we need testing case for constructor? No, Yanhao, you don't need this. Yeah, because simply we'll be testing it through all the other methods. Karina, Nicole had a question. I am also wondering about above. Oh, let me check this. After, how is your exam? So, well, yeah. So let me leave this towards the end because I want first to make sure I finish the lab related questions. So is there any other question related to the lab? Okay, good. So if not, then can you show how you open the terminal in Eclipse in Java? So if you already have it, so assume that I don't have the terminal open here, right? What I should do, if you already have it installed, you just do view, I guess if I remember, window, show view, and then you would have, well, it should be perspective if I remember. I don't remember myself. That's something that is good. Is it in navigation? Right click in the project folder and open here. Yeah, but I was opening it usually from here, but I don't remember. Appearance maybe. Well, show view and console. I guess other, because it might be in the other. And then terminal, yep. And then terminal. Yeah. Or as they were saying, if you want to open the terminal in the same folder, you can just right click in the project and I say there was something like open in terminal, open in local terminal here. Yeah. Right. This is another way of doing it. Well, I guess the one who is asking this question, his main problem is not in finding the terminal. I guess more in that it might not be installed. So what you want to do is here in the help, you can look for marketplace. Let me see, where is that? Eclipse marketplace. And then search for terminal. And then, are you guys able to see the other window? I'm not sure if you're able to see the other window. Yes, oh, that's good. And then if you search for terminal, it will appear for you. And then I already have it installed, but simply here you will be asked to install. Good. Okay, good. So then the question related to the exam. So simply, so let me see exactly what is the question. You can only run one language at a time. Well, in fact, that's not the case, right? So let me show you. So here I already have the Eclipse IDE open for Java, right? If I just open the other Eclipse that I had in my system for C, by just like I was searching Eclipse in my search bar, and just takes a while to open, but it should open soon. Well, come on. Okay, so yeah, this will already be recorded, Nicole. So anyone wants to leave, yeah, I would be answering questions, but we are done with the main content of the tutorial. So feel free to leave, and thanks for letting me know. So simply, the first thing is you can open both Eclipse, the one for C and one for Java, in your machine, because these are two separate binaries. That's the first thing. And really, they have different workspaces even. The second thing is, you even, and I guess that might be my suggestion for anyone that is encountering any problem with Eclipse or related git push or whatever, simply use an online IDE, right? Just take the files, like copy the file code from even your GitHub web page, copy and paste into online GDB. In online GDB, you can have 2 tabs, one of them for Java, one for C, and run this, and it should run, right? That's also a second possible way. A third alternative that I'm trying to explore right now, but well, not yet mature, is through GitHub Classroom itself. I might be able to make it such that you use an online IDE in already inherited in the classroom, right? So it opens something like rebel.it, the compiler that we were using before. But this might require some sign-in, so I'm still exploring. But if this is going to make it easier, then I will do that. If not, simply just, guys, open the GitHub web page. You will find the questions there. Write them down in an online GDB or any other compiler, and then paste them back into the GitHub and then submit, and that's it. I don't want you to suffer any problem back again with the pushes or whatever, right? If you are comfortable with Eclipse, if I were you, I'm going to do this, but it's completely up to you. I will open 2 Eclipse as I have done right now. Let me show you. So right now you already see my, I guess you are seeing my Eclipse for Java, right? So let me switch for my Eclipse for C, which is this one, right? You see this is lab 2 question 7 or whatever, right? I hope you see it open, right? So in your system, you really can have both, because these are 2 different binaries, right? So then, Jan Hao, I guess you had a question about lab 4. So please go ahead.
I was asking for the lab 5, like for that class SLL node.
Okay. So what is your question then?
Can you go to that?
Yeah.
Okay.
I'm already here.
So I didn't see any value of the class. Like you only put the size of it.
Well, what do you think?
So
Where do we usually put the values? Are we putting them in the SLL set?
Oh wait, never mind.
Right?
Yeah, I see.
Okay.
1 second. Like, can we just write a SLL node? Like, can we just put a, what do we call it?
That's
static.
An object of this. So what do you mean by static?
Yeah, why don't you put the size for the static in SLL node? So you can know how many objects.
Well, but size and head are attributes of the set, right?
Oh,
so
no,
for example, yeah, a node is a single element, right? While the size is simply for the set. I will give you one clear example. What if I want to use the same class, which is SLL node, to implement another linked list?
I see. I see.
So you want to make it generic. Like you want to attach the attributes to the object that makes more sense, right?
Yeah. And for the lab 4, can you give us a hint of the last question? Do we
is this
have
the efficient solving one? The one that you are thinking?
Yeah.
Yeah. Let me think. To be honest, because I have been working on this lab, so now I don't remember what I was. Let me try to open this lab document and see now. But I guess you are referring to the efficient solving. So let me think.
Yeah.
What hint I can give? So the hint that I gave in the previous tutorial was that simply, for the 0 elements in your upper triangle, which is the lower triangle of your matrix, you shouldn't consider any values of your vector, right? Like the B1. Why that's the case? Because you will be multiplying by 0, right? That's an efficient way of looking into it. So, which means you need to come up with somehow a mathematical equation that tells you if you are in the lower triangle, then, well, you don't need to multiply, right? And your 1D array is already not looking into those elements anyway, right?
I see.
Yeah, that's the bigger hint for efficient solving, right?
Okay, so I have already got an idea, but I just think it's kind of complex to implement.
If you want, yeah,
mathematical way. Yeah, I did that in mathematical way. Like you literally just do whatever you do in your handwriting. You plug in and then sub back to the previous equation and then
correct. But that means now you will even add the elements that are zeros, right?
No.
Oh no, like, that's then good. Yeah.
So that's the only way to.
Well, it's not the only way. I mean, there might be multiple.
But efficient. I mean,
it might not also be the only efficient way, right? So because also there might be for exactly same efficient running time, you can have different solutions, right? But what you said, so as far as you avoid the zero elements, that is an efficient way of doing it, right?
I see.
Yeah, because you avoid the unnecessary multiplications and additions in this case.
Okay. I see. Thank you.
Welcome. Okay, so thanks everyone, and I guess I will see you all in the lecture in an hour. Thanks and bye-bye.